Hi, I'm Noah, and today I'm going to be talking about avionics software. So, a brief overview of what I'll be talking about is I'll start off describing what is avionics software. Then I'll go into how it differs from traditional embedded systems, then touch on the design/development process, and finish it off by going over some ethical concerns based around avionics software. So, what is avionics software? Avionics software is an embedded software with great reliability concern and safety concerns, and that is used in avionics, so in aircrafts. Now, some examples of avionics software would be navigation systems, primary flight computers, flight control systems, autopilot, and varying other systems and sensors and gauges that you'll see in aircraft. Now, what sets avionics software apart from a traditional conventional embedded systems? Now, the main thing that sets it apart would be that the design and development process of avionics software is highly regulated and optimized for safety and is required by law. You have the DO178C document, which creates these guidelines for how you should develop the software, how you should design it, how it should be tested, and all these different requirements that every manufacturer has to follow to ensure that they can have their software be put on the commercial market and be installed in aircraft. Now, this was set up to ensure maximum safety when software that's going to be controlling things like flight or that might be altering flight courses are going to be taking over the aircraft, and you want to ensure that they're bug-free, they're safe, and they weren't designed poorly. Now, avionics software design is standardized. So like mentioned earlier, you have the DO178C, and all companies have to follow that guideline. And as mentioned earlier, it provides a guideline that the companies can follow and again ensure that everything is made up to code and is safe. And most of the design process is focused around safety, which of course if you're going to be riding in an aircraft, you want the software that might be controlling the aircraft to be designed with safety in mind first, rather than just the functionality. So design. A lot of manufacturers prefer to use the waterfall method of development, and this is good because although it's not very flexible, it kind of matches with the fact that they have to follow strict requirements and safety guidelines. So it puts something that can kind of be matched up with just the guidelines they have to follow. Now, some companies may opt into allowing the developers to go back, adjust requirements, maybe add some new requirements, and be a little bit more flexible. So some companies they may follow waterfall method on paper, but it turns out being more spiral because they'll come back to old requirements and try to adjust them. And some programming languages that you'll see used a lot in avionics software are some of the same that you'll see in traditional embedded systems like C, C++, assembly, some Visual Basic. Ada is very popular with avionics systems. You'll see it a lot in their software, and Java and Python can be used on some subsystems, but generally it's more for when they're going to be creating like a user interface or something that a human will be interacting with, that they'll use Java and Python for that, but not for the core, like the core backend code that will be doing most of the work. So development. A lot of the development is based around human interaction. So what this means is the software that they're going to be writing is going to be obviously used by a pilot, and a pilot will have their piece of software on a gauge that's mixed in with hundreds or a bunch of other gauges and sensors and everything like all in the cockpit. So when they design their software, they don't want it to be confusing. It must be easy to see, easy to use, easy to read. So they take all this human interaction into account when designing the software, because to be effective, it has to be convenient and used, because when something goes wrong or when you're flying a plane, you don't want to have to figure out how the software works or figure out what the software is telling you. You just want to be able to look at it and know exactly what it's telling you and how to use it. So they also take possible hazards into account. So when they complete their analysis on when they complete their analysis on requirements, they'll look into the software and they'll look into potential hazards that could come from the software. So if you have an autopilot system, they'll look into like what if the autopilot system fails? What if it shuts off? What if something, turbulence happens? Like what will happen when these things, like what are some potential hazards that could affect their software or be caused by their software? And they'll take these hazards and they'll go through and they'll add them as requirements. Like they'll find fixes for them and they'll put them as a requirement to ensure total safety of their product. And so due to the design process being a legal requirement and highly regulated, there's a lot of documentation that goes along with this, which also comes back to like more traditional models like waterfall method and spirals, that they include a lot of documentation with them compared to something like agile, which usually doesn't use as much documentation. And because of this, they need a lot of documentation because if something goes wrong with their software or they're being audited or something, you want to have a paper trail of every safety precaution that you took and every design choice that you made so that you can show it to a regulatory body if you're, to show that your code and your software is up to spec and is not dangerous. And code reviews, while writing the code for this, are a necessity, as they are with most, if not all, professional software, commercial software that's out there. But for avionics software, you especially want it because you want to make sure you can catch logical errors, programming errors, and anything else before you go into testing would be great, because then it's easier to fix if you have someone come over, read your code, and they notice some errors or you're not following design standards. And so they're a necessity to ensure everything is written as it should be. So testing. This part is probably one of the most important parts of the design and development process of aviation software, because you want to make sure that the software works as it should on a plane, because obviously you don't want your primary flight control or your flight computer to fail while you're in the middle of, trying to land or fly. So what they'll do is they'll first spread a lot of unit tests throughout their code. And what this will do is it'll help ensure that it'll help catch any logic errors or programming or simple programming errors that, although the errors are simple, they may cause the program to crash or may cause bugs that could interfere with how the software is supposed to work. So these unit tests will be spread throughout. They'll catch those errors before they occur on live testing or, God forbid, when it's actually in release. And so then after that, they'll move on to integration testing. So they'll test it to make sure that with the physical hardware and everything else installed, that the sensor, if it's a sensor or if it's a flight control computer, everything, it's reacting to what it senses or to what it's supposed to correctly, and make sure all of its most important features are working properly. And finally, they'll move on to black box testing. The unit will be installed and it will be working in tandem with other units. And you want to check that when it's working with other parts of the software, with other sensors and other software that will be on in like a normal commercial aircraft, you want to be sure that they won't interfere with each other, that one sensor might read something and it might be put into another sensor, which might cause errors, because these kinds of errors can cause planes to crash. So that's why testing is so important with this, in making sure all the testing is organized and documented and everything, is because you don't want one test to slip through and then that the part of the functionality that test was supposed to ensure worked doesn't work, and then you have a plane crashed on your watch. So that kind of ties us into ethical issues. So because avionics software is related to aircraft, a failure to find a bug may lead to large financial losses, with people dropping you from a contract, and on the worst case scenario, loss of life. So the lazy development can lead to a lot of bugs, and these bugs can lead to real world effects, more so than like on a phone. If there's a bug on your software and your application crashes or whatever and you open it and then the company will patch it, but if your flight control computer is bugged and it shuts off, you might have a plane going down or you might have people dying. So cutting corners with this kind of software could happen, and for trying to save money, and it can cost people's lives. So with the 737 MAX 8, a lot of people have heard about that in the news. There were some software changes and some software added that Boeing stated that the pilots didn't need to be retrained. And one of the theories that was going around with why the plane crashed was that there was an issue with the software, and it was causing the plane when it was when it was taking off, it was trying to adjust the plane's pitch, and the pilots that weren't familiar with the software because they weren't familiar with the Max 8, they might have been familiar with the normal 737. They didn't know what was going on, and they didn't know how to correct it, which caused the plane to stall and crash. So there's another ethical concern that could be seen with aviation software. And finally, a lot of the software handles critical functions of the aircraft, like flight control computers, and like previously mentioned, the 737 MAX 8 adjusted pitch of the aircraft. And this could leave an aircraft vulnerable if they don't write the software with security in mind. Now, there's probably a low chance that someone is going to be able to hack an airplane or something, but if if possible, again, like mentioned a lot before, if there's a security vulnerability or something and someone is able to get into it, again, this software is controlling an aircraft that most likely will have a lot of people in it and could cause a lot of problems. So in the end, there are some ethical concerns with this, and yeah, that's aviation software. Thank you.